Light-emitting diodes, LEDs, are semiconductor devices that work almost like photovoltaic solar cells in reverse. A semiconducting material is infused with impurities to create a p-n junction. Setting the P side to a higher voltage than the N side causes charge carriers, electrons, and holes, places in the crystal lattice where electrons are absent, to flow into the p-n junction. If an electron meets a hole, it falls to a lower chemical energy level and releases electromagnetic energy in the form of a photon, a particle of light. The wavelength of the photon emitted depends on the semiconductor material. Today, LEDs are available that emit wavelengths ranging from the infrared to the ultraviolet. Most suitable for interior lighting are so-called white LEDs. These are modified blue LEDs in which the semiconductor chip is coated with a phosphor that absorbs the blue wavelength and emits a broad spectrum centered around yellow. The human eye perceives a combination of blue and yellow as white. LEDs currently account for a negligible fraction of lighting because of performance and cost issues, but these are improving rapidly. Light output from a single LED doubles every 2 years, cost per light output halves every 3 years, and the luminous efficiency doubles every 6 years. Sales of high output LEDs have expanded 42% from 1995 to 2005. They are now common in traffic lights, vehicle lights, flashlights, retail display cases, and backlights for screens on cell phones and notebook computers. In comparison to fluorescent bulbs, LEDs are longer lasting, more robust, faster responding, easier to dim, smaller, and mercury-free. LEDs are destined to become a larger segment of the lighting market as their technology advances. High-intensity discharge lamps include mercury, metal halide, and sodium lamps. They produce light from an electric arc between tungsten electrodes housed inside a fused quartz or high melting point glass tube. This tube contains both an inert gas, usually argon, and metal salts. An electronic or magnetic ballast usually generates a high voltage that ionizes the inert gas. This starts the electric arc, heats the inner tube, and vaporizes the metal salts to produce a light-emitting plasma. Once the plasma forms, the ballast sustains the arc at a low, steady current. Mercury lamps emit light that is rich in the ultraviolet and blue wavelengths. This casts a ghostly pall over the illuminated area, as well as requires UV filters in the outer glass envelope to minimize dangerous radiation. Metal halide lamps add other chemicals to the mercury, such as sodium iodide and scandium iodide, that broaden the spectral distribution of light emitted, giving it the appearance of natural daylight. These lamps provide illumination for night sporting events. Low-pressure sodium lamps emit nearly pure yellow light. High-pressure sodium lamps also contain mercury, and the blue light from the mercury, in addition to the accentuation of minor wavelengths from sodium under pressure, gives these bulbs a whiter appearance. High-intensity discharge lamps are relatively expensive, about $150 to $250 per unit. That includes a fixture, ballast, and bulb. Prices do not vary much with size, from 70 watts to 400 watts, and so most installations have a few large units rather than many small units. High-intensity discharge bulbs account for only 1.2% of global lamp sales, but they deliver 29% of the electric light because they have higher efficacy, higher average power, and longer lifetimes than most other lighting sources. Their high purchase price, large size, and hot bulbs make it unlikely, however, that high-intensity discharge bulbs will penetrate further into residential lighting markets, except in closet greenhouses.